Hello friends, welcome to lecture series on matrix analysis with applications. So, in the last lecture we have seen some special matrices like symmetric matrices, skew symmetric matrices, Hermitian matrices and skew Hermitian matrices. We have seen that what are the important properties of these matrices. So, there are some more special matrices which we will see in this lecture and what are their properties. Okay. So, first is orthogonal matrix. Now, a square matrix A with real entries whose columns and rows are orthogonal unit vectors, that is A transpose A equal to I. An orthogonal matrix is basically a square matrix where A inverse is nothing but A transpose. So, for such type of real matrices are called orthogonal matrices. Now, for example, this matrix, the first matrix, okay, we can easily verify. You see, the matrix says simply A is equal to, you see, cos theta minus sin theta and it is cos theta. When you take A into A transpose, it is A. What is A? It is cos theta minus sin theta and it is cos theta. And when you take transpose of this, it is cos theta minus sin theta and cos theta. So, this row into this column, so cos square plus sin square, which is 1, this row into this column, cos into sin minus sin into cos is 0, this row this column, that is sin into cos minus cos into sin is 0, and this is sin square plus cos square, which is 1. So, it is identity matrix. So, that means A inverse equal to A transpose and hence it is orthogonal matrix. Okay. However, if you see the second example and if you take B into B transpose for this matrix, it is not an identity matrix. So, this matrix is not an orthogonal matrix. Now, what are the properties of orthogonal matrix? The first property is the determinant of orthogonal matrix is either plus 1 or minus 1. So, it is very easy to verify. You see, orthogonal matrix are simply A into A transpose is equal to identity. You take determinant both the side, determinant of A into A transpose is equal to determinant of I, and this implies determinant of A into determinant of A transpose is equal to 1 because determinant of identity is 1. Determinant of A and determinant of A transpose are same because by changing rows and columns it will not change the value of the determinant. So, we can say that it is determinant of A into determinant of A equal to 1. And this implies determinant of A square equal to 1, which means determinant of A is simply plus minus 1. Okay. So, from here we can say that determinant of an orthogonal matrix is either plus 1 or minus 1. So, this is the first property. Okay. Now, all eigenvalues of a real orthogonal matrix have modulus 1. Okay. So, what does it mean? How we can prove it? You see, you can take any orthogonal matrix with real entries and its eigenvalues always have modulus 1. So, this is very easy to verify. You see we have a orthogonal matrix, definition of orthogonal matrix is A into A transpose equal to identity or it is also equal to A transpose A. Okay. Now, you take Ax equal to lambda x is not equal to 0. So, this means lambda is an eigenvalue of A and corresponding eigenvector is x. Now, you take conjugate both the side because lambda may be complex entry also, complex value also. Now, this implies because A is real, so A bar is itself. So, it is A into x bar is equals to lambda bar x bar. Now, you take transpose both the sides. So, if you take transpose both the side, it will be x bar transpose A transpose is equal to lambda bar x bar transpose, because lambda bar is a scalar quantity, its transpose will be itself. Now, this implies x bar transpose. Now, you multiply both sides by A, matrix A, post multiplication. So, you get this expression. A transpose A from this expression, from expression 1 is identity. So, this implies x bar transpose identity is equals to lambda bar x bar transpose A. Now again you post multiply both the sides by vector x. So this implies x bar transpose x is equal to lambda bar x bar transpose Ax, and Ax is nothing but lambda x from 2. Okay. So this implies x bar transpose x is equal to lambda bar x bar transpose lambda x, because Ax is equal to lambda x from 2. So this implies 1 minus mod lambda whole square into x bar transpose x is equal to 0, because lambda into lambda bar is mod lambda square. Now x bar transpose x is never 0, because if x is, suppose this vector x1 x2 up to xn, then x bar transpose x will be x1 bar, x2 bar and so on up to xn bar into x1, x2 up to xn. And when you multiply this row with this column, this is mod x1 square plus mod x2 square and so on up to mod xn square. And it will be 0 only when all xi's are 0, because modulus are the positive quantities. Okay. So this will be never be 0, because x is not 0. Because x is not 0, hence this is not 0, because this is 0 only when x is 0. Okay. So this quantity is not 0, so this implies mod of lambda is equal to 1. So we can say that all the eigenvalues of an orthogonal matrix have modulus 1. Okay. Now the next property is inverse of an orthogonal matrix is also orthogonal. Okay. So suppose you have A which is an orthogonal matrix. So since it is an orthogonal matrix, so what does it imply? It imply A into A transpose is equal to A transpose A is equal to identity. Now you take B as inverse of A, and you have to show that B is also orthogonal matrix. So we have to prove that B is also an orthogonal matrix. Okay. So in order to show this, what we have to show? We have to show that B into B transpose is equal to identity, or B transpose B equal to identity. Now what is B? B is A inverse. You take this side, left hand side, into A inverse whole transpose. This is equal to A inverse into A transpose inverse. This is equal to A transpose into A whole inverse, because A into B whole inverse is B inverse A inverse, and this is equal to I inverse, because A transpose A is I. So this is I. So similarly this is B transpose B we can show is equal to I, and hence we can say that B transpose is equal to B transpose B is equal to I. So this implies B is also an orthogonal matrix. Okay. So these are the properties of orthogonal matrices. Next is unitary matrix. Now complex unitary matrix is a complex square matrix in which conjugate transpose is equal to its inverse. If you take the conjugate transpose and is equal to its inverse, then we say that that matrix is a unitary matrix. Okay. Now for example, you consider this matrix A. So what is matrix A here? Here A is 1 upon under root 7 times, 1 upon under root 7 times, it is 1 plus 2 iota, 1 plus iota, 1 minus iota and minus 1 plus 2 iota. Okay. Now if here you take A conjugate transpose which is AH, we denote it by AH. If you find this, it is 1 upon under root 7, it is 1 minus 2 iota, 1 minus iota, 1 plus iota, minus 1 minus 2 iota. Now if you take A into AH which is A conjugate transpose, it will be equal to 1 upon 7 times 1 upon 2, 1 plus 2 iota, 1 plus iota, 1 minus iota, minus 1 plus 2 iota, it is A, and A conjugate transpose is 1 minus 2 iota, 1 minus iota, 1 plus iota, and minus 1 minus 2 iota. Now, when you multiply these two matrices, what we obtain? You see this row or this column, this is nothing but 1 plus 4 plus 1 minus 1. Okay. When you multiply this row with this column, it is okay. Okay, we have you see when you find the A conjugate transpose here, so you have to take the conjugate also, you have to take the transpose also. So, when you take the transpose here, so what you will obtain? It is 1 plus iota and it is 1 minus iota. You have to take the conjugate and then the transpose also. So, here also it is 1 plus iota and here it is 1 minus iota. Now, when you multiply this row with this column, it is 1 plus 4 and it is 1 plus 1. Okay. When you multiply this row with this column, you can verify easily that it comes out to be 0. You can verify. And this row, this column, when you multiply this row with this column, it is 0 and it is again something 7. So, what we obtain is simply identity. This you can easily verify by simple mathematical calculations. So, we can verify that A into A conjugate transpose is identity, hence we can say that A is an unitary matrix. Okay. Now, if you see, if you take this matrix B and if you multiply this matrix B by its conjugate transpose, then it is not coming out to be an identity matrix. So, we can say that it is not a unitary matrix. Now, what are properties of unitary matrices? The first property is modulus of determinant of a unitary matrix is 1. The second property is the eigenvalue of unitary matrix are of magnitude 1. Okay. So, this property we can easily show. You see, this follows on the same lines as we did for orthogonal matrices. You see here Ax equal to lambda x, x is not equal to 0. You take bar both the sides. Now, you take transpose. Okay. When you multiply both sides by, now multiply both sides by matrix A post multiplication. A bar transpose A is identity. Again post multiplication by vector x, and it is x bar transpose x is equals to lambda x bar transpose lambda x, lambda bar, and it is 1 minus mod lambda square, again same lines, following same lines as we did for orthogonal matrices. Now, since x bar transpose x is not equal to 0, so this implies mod lambda is equal to 1. So, like orthogonal matrices, unitary matrices also have eigenvalues of unitary matrices also have modulus 1. Now, square matrix, now idempotent matrix. A matrix A is said to be idempotent if A is square equal to A. Okay. You can easily verify if you square this matrix. So, you get matrix itself, I mean A itself. However, square of this matrix is not an idempotent. So, these are very easy to verify. Now, what are properties of idempotent matrices? The first property is, with the exception of identity matrix, an idempotent matrix is singular. Okay. Identity matrix is idempotent, you see I square is equal to I. Okay. But if A is not equal to I, you see idempotent matrix is what? A square equal to A. Suppose A is not equal to I and A is non-singular. Okay. Non-singular means inverse exists, and if you apply A inverse both the sides here, it is A square into A inverse, which is equals to A into A inverse. it means A is equal to identity, which is not here, because A is not equal to identity, contradiction. So that means if A square equal to A, that means an idempotent matrices, okay, and if A not equal to I, it must be singular, because if it is non-singular, then we are getting a contradiction, okay. So that means an idempotent matrix excluding identity matrix is always singular, okay, that is inverse does not exist. Next is its eigenvalues are either 0 or 1, okay. So again let us try to prove it, because A square equal to A, now Ax equal to lambda x, x not equal to 0. So that means A square x is equals to lambda square x, as we already know this thing, and okay. So that means, what we have concluded from here, we have concluded that lambda square is equals to lambda, because A square equal to A. So we have concluded lambda square equal to lambda. So lambda square equal to lambda, so it implies lambda is either 0 or 1, because A square is equal to x, because here you can see that A square equal to A, okay, is equals to lambda square x, and this implies Ax is lambda x, and this implies lambda minus lambda square times x is not equal to 0, and since x is not equal to 0, so lambda square equal to lambda, hence lambda is either 0 or 1. Now since eigenvalues are either 0 or 1, so sum of eigenvalues which is equal to trace of a matrix is always an integer, in fact a positive integer, okay. So trace of an idempotent matrix is always a positive integer. Next is nilpotent matrices. Now a nilpotent matrix is a square matrix n such that n raised to power k is 0 for some positive integer k, okay, and the smallest such k is called an index of the matrix n, okay. So suppose you consider this matrix, okay. So this matrix is basically, this is 0 3 1 0 0 3 1 0 0 2 0 0 0. Now when you take a square of this matrix, this is not equal to 0, I mean 0 matrix. When you take a square of this matrix, it is 0 3 1 0 0 2 into 0 0 0 into 0 3 1 0 0 2 0 0 0. Now you can easily verify this row, this column is 0, this row, this column is this row, this row, this column is again 0, this row with this column is 6, okay. This row with this column is 0, this row with this column is 0, this row with this column is 0, this row with this column, all other entries are 0. So let us check this entry once again. So this row with this column, or the last column, this row with this column is 0, it is 6, it is 0, so it is 6. Now when you find a cube of this matrix, that is A into A square into A. So what we obtain, this row, this column is 0, this row, this column is 0, this row, this column is 0, and all other entries are 0. So it is simply a 0 matrix. So what we have concluded? We have concluded that this A matrix is a nilpotent matrix of order 3, okay. Now what are properties of nilpotent matrices? The first property is the only eigenvalue of n is 0. I mean if n is a nilpotent matrix, it has only eigenvalue of this is 0. So that is easy to show, you see. Suppose n is a nilpotent matrix, okay, then that means nx is equal to lambda x, x is not equal to 0. Then n raised to power k x is also equal to lambda raised to power k x, okay, and n raised to power k is 0, because n is nilpotent matrices. So 0 is equals to lambda raised to power k x. So this implies lambda equal to 0, because x is not equal to 0. So the only eigenvalue of nilpotent matrix is equal to 0. So this can also be proved. Suppose Suppose n is a nilpotent matrix and lambda is not equal to 0, let us suppose. So, if lambda is not equal to 0, then we obtain then nx equal to lambda x for x not equal to 0, n raised to power kx is equal to lambda raised to power kx. Now, this 0 is equal to lambda raised to power kx, and this implies this is a contradiction, because lambda is not equal to 0, x is not equal to 0, which is not equal to 0. So, this is a contradiction basically. So, this means lambda cannot be lambda cannot be, I mean cannot be, the only eigenvalue of lambda is 0 only, it cannot be different from 0. Okay. The next is the characteristic polynomial for n is x raised to power n. Now, since all the eigenvalues of lambda, all the eigenvalues of n are 0, so the characteristic polynomial of n will be lambda minus 0 raised to power n equal to 0, because 0 is the only eigenvalue of n. Okay. So, that is why it is x raised to power n. Now, the minimal polynomial of n is of course x raised to power k, where k is less than equal to n, because minimal polynomial is the lowest degree polynomial which satisfy n. Okay. Now, next is the index of an n cross n nilpotent matrix is always less than equal to n. Okay. Index is always less than equal to n, that is very easy to show, because Cayley-Hamilton theorem is always satisfied. If the minimal, if this k in the minimal polynomial is less than n, so that will be the order, I mean index of the nilpotent matrix. Otherwise, by the Cayley-Hamilton theorem, n is the index. So, this point can easily be verified using the using these 2 points. For example, every 2 cross 2 square matrices squares to 0 always. Okay. 2 cross 2 non-zero matrices in fact. Okay. Now, the determinant and trace of nilpotent matrix is always 0, because all eigenvalues are 0. So, trace will be 0, sum of eigenvalues, and the determinant will be 0, which is equal to product of the eigenvalues, of course. Okay. So, consequently, nilpotent matrix cannot be invertible. The only nilpotent diagonalizable matrix is 0 matrix. Now, next is Grashe-Goryan theorem. Now, what is Grashe-Goryan theorem? What it states? Let us see. The modulus of the largest eigenvalue of a square matrix. If you want to see what is the largest eigenvalue of the modulus of the largest eigenvalue of a matrix, then this theorem, by this theorem we can find at least the range. The modulus of the largest eigenvalue of a square matrix cannot exceed the largest sum of the moduli of its element along any row. Since the eigenvalue of a matrix and its transpose are same, so the theorem is also applicable to column also. So, what this theorem means basically? This theorem means suppose you have matrix like this, say 1 2 3 4 0 minus 1 minus 2 1 6. So, this theorem states that modulus of lambda is eigenvalue, largest eigenvalue of this, it will be less than equals to maximum of mod of 1 is 1, mod of 2 is 2, mod of 3 is 3, that is 1 plus 2 plus 3, 4 plus 0 plus 1, because modulus of minus 1 is 1, and it is 2 plus 1 plus 6. So, this is equal to maximum of, it is 6, 5 and it is 9. So, which is 9. Now, when you see the column, you see mod lambda is less than equals to maximum of column, when you see it is 1 plus 4 plus 2, 1 plus 4 plus mod of this is 2, it is 2 plus 0 plus 1 and it is 3 plus 1 plus 6, which is 10. So, we can say that mod of maximum lambda of this matrix is less than equal to I mean 9, the intersection of these two. Okay. So, how can we prove this theorem? How can we show this theorem? So, proof is simple. You can see, you see if you have you take Ax equal to lambda x, x is not equal to 0. Now, you suppose x is suppose x1 r, x2 r and so on up to x say nr, where it is which is not equal to 0. Okay. So, you see A is which matrix? A is A11, A12 and so on up to A1n, A21, A22 and so on up to A2n, and so on An1 and so on up to Ann. So, what we will obtain? You see, you have to multiply each row of A with x. So, this implies it is ai1 x1r plus ai2 x2r and so on up to ain x n r is equal to lambda r x I r, and this I is from 1 to n. Okay. When you put I equal to 1, it is a11 x1r, a12 x2r and so on up to a1n xnr, which is lambda r x1r, and similarly for I equal to 2 to n. Now, you take modulus both the sides and mod of this, because mod of a plus b is less than or equals to mod of a plus mod of b. So, we can say that is less than or equals to mod of ai1 into x1r plus mod of ai2 into x2r and so on mod of ain into xnr. Okay. Now, let x, suppose SR, it is SR is a maximum of mod x1r, mod x2r and so on mod xnr. Suppose out of maximum of modulus of these xi's, xsr is a maximum one, okay, and of course it is not equal to 0 because x is not equal to 0. So, maximum can't be 0. Okay. Now, you can divide, now you divide this equation by this by mod of this xsr. When you divide both the sides, so inequality will not change, and it is less than or equals to mod ai1 plus mod ai2 plus and so on plus mod ain, because mod of xir upon mod of xsr, okay, is less than or equal to 1 for all I, because this is a maximum one. Okay. So, we can get this inequality. Now, this is valid for every I. So, this is valid for I equal to s also. So, for I equal to s, what we obtain, mod of lambda s is less than or equals to mod of as1 plus mod of as2 plus and so on mod of asn. So, which is equals to summation of j varying from 1 to n mod of asj. Now, if it is less than or equal to sum of this, so it will be less than or equal to maximum of maximum over I, basically sum of j from 1 to n mod of aij. Okay. So, what does it mean? It means that sum of some modulus of sum of the rows. So, we can say that the eigenvalue of matrix A is less than or equals to maximum of sum of the rows. Now, we have one result based on this, that is, for each eigenvalue lambda there exists circle with center ASS and radius this such that it lies inside the circle or on its boundary. Okay. Let us verify this result by an example. Suppose we have this matrix A. What is the matrix A here? The matrix A is 1 minus 1, 2 minus 2, 2. So, what are eigenvalues of this matrix? If you quickly see, so eigenvalues of this matrix are simply sum of eigenvalues is 0 and the product of eigenvalue is simply minus 1 and plus 1 plus 2. Okay. So, it is 1. So, eigenvalues, what are eigenvalues then? That we can easily find out you solving these two equations. So, these are nothing but you see minus lambda 1 square is 1. So, lambda equal to plus minus iota. So, one lambda is iota, another lambda is minus iota. This you can easily verify. Sum is 0 and the product is 1. Now, if you see lambda minus ASS here, first the first row is 1, okay, is less than equals to sum of these two other than diagonal elements, that is 1. Okay. Now, lambda plus 1, center here is minus 1, less than equals to, excluding this entry, because we are in excluding j equal to s here. Okay. So, that is why, so it is equal less than equal to 2. Now, when you draw these two, here center is 1 and radius is 1, center is 1, radius is 1 means this circle, and here center is minus 1 and radius is 2, radius is 2 means this circle, something like this. Okay. Now, when you see the first lambda, which is iota, its modulus is 1, its modulus is 1, so it is inside this circle, that means inside the second circle, and its eigenvalue, its modulus is also 1 and it is also inside the second circle. Okay. So, what this is what this theorem states, that there exists for each eigenvalue lambda, there exists a center ASS and a radius such that it lies inside the circle or on its boundary. So, the same theorem can also be verified on this example. Okay. So, hence we have seen that what are the properties of some special matrices like unitary matrices, orthogonal, idempotent and so on, and also how we can find out the range of the eigenvalues this matrix is given to us using Green's choice.